course, I haven't got my mic on. Okay, so I'll just try to start again. So I've had accidentally set my encoder settings to use H.265 instead of H.264. So I was happily sending a bunch of data to Twitch, but they didn't. They weren't having any of it. So anyway, we're here now, and I'm just catching up on where we were at last time. Well, where we got up to last time. So just to recap, we're writing a Go package to encode and decode SCTE35 messages. SCTE35 messages are they're binary encoded, and they are used in live streaming to signal ad breaks. I've got my iPad here, so it might be a bit of fun to get that going. Where we're up to is where one of the messages that you can send in this protocol is called a splice info. Splice info section, I'll just call it splice info for now. And that's represented in this struct here. Now what we're actually doing is we're just working on the code to decode a message. So we have these fields here, but when we're doing the wire format, there's actually a bunch of other stuff. So there's stuff that users of the package don't need to see. These are things like the length. There's some metadata, basically. Metadata. And then there's the stuff that we're actually going to be looking at. So the first thing we care about is the SAP type. And then there's going to be some encryption, maybe. And what we're working on specifically right now is we're trying to decode the tier. And I'm running into some problems there for some reason that I can't quite work out yet. So basically, let's see. So I've got some tests running now. We're just working through bit by bit, checking that when we decode a known good message, and a known good message as in that it's encoded correctly, we just go through bit by bit, byte by byte, trying to work out if we get the values that we expected. So here's our code that does all that. So right now we are, I'm just going to get rid of this. So just going to re-index all of these because I think I'm having a bit of a problem there, but anyway. So this will be 0, 1, 1 and 2, 3, and then this is 4, 4, 4, 6, 7, 8, 9, okay. So what we've got right here is let's start by looking at the example that they give us and the values that we want. So we're going to go down to our example here, and here are the fields that we want to find. So the decoded length we don't care so much right now. Table ID is the first byte, which we skip over, we don't care. The next, that's table ID, the next, what do we got here? 2 bits. here. We also don't care about because these are constant values in the spec. So we can happily skip over that too. So the next one that we do care about is this SAP type here. So let's see if we decode that correctly. So go to our test. Now the value that we want here is none. So let's do a very simple specific check. So we decode the splice info, and then we go if one.sap type is not equal to the thing that we got. Sap type. That seems correct to me. Want none, got none. Ah, here we go, look at this. See, so this is so anything greater than OX3 is actually invalid. So let's, yeah, so we'll do this. There we go. So there's our first problem. Easy. So we're for sure doing something wrong here. So we're skipping these 2 bits and we want to extract the value out of those 2 bits. Oh no, of course this is incorrect because we're, yeah, no, because the value of this is, yeah, no, this is totally wrong. Okay, let's fix this up. So what we really want here is, if I go back to my pen and paper, what we're doing is we're getting a value that's, yeah, no, this is all wrong. So we're gonna need the, we're gonna do some bit shifting instead to get the value that we want. So let's just call this st set type or yeah, anyway, let's do that, and then is one and with or what we could do is we could actually, yeah, this, and then we shift. So we've got now those 2 bits and we've zeroed out everything else. So the next thing we want to do now is shift everything over. So we're going to go shift it, let's say, to the right 4 positions. And then we can do, how do we do that? Yeah, like that. Is that, oh God, I'm just, it's, I've only just started writing, doing this now, so I was doing other stuff before. Right, so let's see that. So the info dot is that. I believe that's correct. So let's see. Oh yeah, okay, and then we convert it into our custom type. Awesome. Okay. We have the expected value. So I might be able to do this in one line. I'm not sure whether that's really clear or unclear if we need to split this thing out, but anyway. There might even be a neater way to do this. I'm not super familiar with the working at this kind of level. So anyway, let's move on now to, let's actually try decoding the length, because we have it to do here, and that's going to be the next, those are the next bytes and bits. So we go down here. So it looks like it's 52. So let's, I'm tempted to actually oh no. Okay, what we can do is we can just print a standard error for the moment, and then see how we go. So if we go back to our bit layout, there we go. So we've got the 4. Okay, so from the byte of index 1, so let's draw a diagram, might be easier here. So the 1, and then we're also going to have to access stuff from the index 2, something like this, and then we're going to have a like that for each byte. So we've already used these, oops, we've already used these bits, so we'll just have those as like that, and then we want 4, and then we want all of this, so 4, 5, 6, 7, 8, 9, 10, 11, 12. So and in hex, this one is OXOF, and this is OXFF. So we could sort of bit mask, so to get the integer out, we can just get a uint 16 from those two, but then mask out the first 4 bits like that. So like strip off the first 4, or rather the leftmost 4, whichever way first and last. I'm not quite sure what the right word for that is. So let's do that. So I'll just call it length is you can get that, decode a big endian. That's the way it's ordered, and we're going to get a uint 16 out of it, and then we're going to get from buff, as we said, from buff 1 and 2. And then we'll just do the mask because it's a and then let's just print this out to check how we get our actual number. Let's do it just to print out the length. Don't want to forget that. Okay, let's go. Whoa. Oh, prints a standard error. $47. Not quite. We want 50. In our example, we want 52. Hey, thanks for the follow, C. Perino. Thanks for joining us. It's nice to do this with some other people, so thanks. It's cool. So this doesn't seem to be quite right. Sorry about the barking. I mean, I shouldn't say sorry. This poor dog is barking almost every day, poor thing. Let me just see. I might actually just get my sunglasses. 2 seconds. Okay. Hey. So, let's see what's next. We've got our SAP type finally decoded okay. We've just trying to decode the section length. So that's really the length of or how many bytes we've got remaining after this particular point. So we're expecting to get 52, but we're actually getting 47. So just to make debugging a bit clearer now, let me just comment out that stuff. All right, we're getting, no, still more junk that we don't really want right now. Okay. Oops. Great. Okay, so let's get this. Let's just limit what we're running because we don't care about the encoding yet, because we're not quite there yet. Great. Okay. So we're getting 47, but we want 52. Let's just check that our logic here for doing the masking is correct. To me, that seems correct. So if I go back to this iPad here, so these, say, these bits here were all used for the, yeah, we had some metadata and the SAP type. So that means that what we've got left is, yeah, we want to grab all those other values. I'm going to grab all these. So to me, I feel like I'm not sure. Anyway, what I might do is print the okay, maybe what I need to do is actually do a bit mask all the way back here. And length is still 47, so I get the same value. Yeah, let me print out a binary of that. Just print all 16 bits. Okay, let's have a look. And the value that we want is 52 in binary. So we can just spin up our little test. 52. So what we're running right here is just a little local Go playground. All right, so that's 52 in binary, and what we're getting is that. So it looks so 1, 2, 3, 4, 5, 6, 7, 8. So there's the 8. Am I going to do this little endian? Is that what I'm doing really wrong here? I often always get confused with this. No, okay, obviously not. So we want 12. Yeah, I mean this I just okay. So if I look at this thing again, I mean to me, we've got we've read these. We read all these, and then the next bit is we'll need to read just those 4 bits, and then all of them from the next byte to get 12 bits. 4 plus 8. So the next thing would have to be section. Let's read that again. Section length. Let's double check. Section length 52. Yeah. Two, three, 4. gives us. Yep, that's expected. And then let's now make this one. One, 0, 0. This actually looks, yeah, that looks, what do we want? Ah. 1, 1, 2. It's totally different. Totally different value to the example. Print out both bytes. Look for the, let's actually get a search for the number 47 to see if, oh wow, what are our chances that actually we're doing the next example? Look at that. Let's double check. BMW, bro, oh, you'd be fucking kidding me. We're looking at, this whole time I've been looking at the wrong example. No wonder the values weren't adding up, or that they weren't matching. Fuck. I could not believe it. This whole time we were working on the wrong example. So, jeez. All this. Yeah. Okay. Yeah. So that's sample 14 point, how do they call this? 14.1.1? Sample 14.1. Okay. Obviously, we're going to have a table that, just goes through all of these. Yeah. So we were just fine all along. So we'll just do length. Okay. Great. So now we know the length of ahead of time, so we can just happily, kind of, or we can even check, we could do something like if the just double check that we'll do less than not sure whether this is really an error that we want to check for, but and we could actually just compress these error cases down. So length, but we will have len of buff. Let's just do this. So it's not equal to length. Oh, that's off. That's one. No, that's. Oops. The converted. There we go. Ah, 55. Okay, so we'll, because we've so now what we can do is we'll reslice after this. So because we've done 0, 1, and 2, so we've done those 3 bytes, so we can get rid of or is it going to be from 3? Anyway, let's just do 3. Yeah, okay, so we need it from 3 onwards so that we cut out byte index 2. Great. Okay, there we go. Great. So now we can and then we can even, let's just do reslice again, I don't know. Oh, no, let's just, no. Okay, so we're going along and now we're going to need to redo the index on these. So this is left over from this byte, and then we're going to go down and just increment, reassign that 4, 5, and then that's going to be the next byte along, because we've read a uint 30, well, I have 33 bits out of here. Going to get that one. And then let's read 7, 8. I think that's all the bytes that we care about. Ooh. Okay, so we can actually go to where our test is failing, which is finally failing on the decoding. So that debug print if we still have it. No, I think we got rid of that. Yep. Okay. Looks like we want this value, but we got this. So we're actually we're very close. Looks like we might need to read it the other way around. So doesn't seem quite right to me, but see if that's any different. Nope. Is this little endian? But then no. Okay, let's check the spec again just to make sure that we're reading this tier correctly. So here. So we've read the encryption info from that byte. We've skipped over the version. So 740 is 5 bytes. Yep. So 1, 2, 3, 4, 5. Next is the CW index, which is at 6. And the tier is going to be the next 12 bits. So we get 8 bits out of here, and then 8 bits out of there. That's 16, but we only want 12, so we mask the last, so mask the rightmost 4 bits. So if we did do our diagram again, this time it looks a little bit different. So I'm going to look so what's our index now? It's going to be we're going to be reading from 7 and 8. So 7 and 8. 7. Yep. So we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then blank 2, 3, 4. So that's O, X, F, F, and this is O, X, F, O. So the bit mask is going to be O, X, F, 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 O, which I'm pretty sure is what I've got. Yeah. Yeah. Yeah, I'm not quite sure how this thing works. I feel like it, and the thing is that it cannot, that number's just way too big. The maximum value is, yeah, 4095, so it can't, that's something wrong here. Oh, this is because because tier is actually then, yeah, in Go is a little endian. So that means that what we really want is, if I go back to the pen and paper, we've got this and this. But really we only need this mask. So I think, let's just try that and see what that looks like. So we're going to go, let's just do this. So here the mask would be X, B, F, O. No, same thing. No, not that either. So there is some weird part of the spec that I read that basically just says something like the tier could really be anything, but if it is anything, it always needs to be 4095. So something odd like that. It wasn't totally clear. So if I go to the information on tier, on the tier field, oh shit. Just read this. Oh no, let's keep that. Let's keep that there. Okay. Messages to authorization tiers. The field may take any value between 0 and that. Yeah, not quite sure what's going on there. I feel like the logic is correct. There might be some other sort of, like extra detail in this spec. Certainly this. Maybe we can skip the tier, or rather just let it error and then keep going along for the next bytes and just see if we run into, because we don't need to quit the test here. We can just keep going and checking all the other bytes. So I'd say let's do that. So next up, if I remember rightly, we have a 12-bit integer that is telling us how long the next field is. So it's going to be we're going to now look at start decoding the command, which we can do. We haven't written the code for that, but should be okay. Since we can just decode the type easily with a byte, do a switch statement on it, and bang, we're good to go. So let's get this command length, because that might be handy. It certainly caught some errors before, I think, even though we weren't going to use it. It's good for us. Let's just I want to do OX. Oops. Okay. We can just reuse this length equals decode out of here. So we're now going to add the next 2 bytes. So 4 bits out of that, and then let's just do it straight away. So the 4 bits out of there is going to be, the rightmost bits will be those, and then all of the next byte, because we need 12 bits. So that's 4 plus 8 is 12. There's our okay. Now, just for now, we can just print out the value, because I know that the example gives us a value that we should get. And I think it's actually, I think we can just continue like that. Yep. 5. Command length. 5. Awesome. We're getting there. I think. Wait, is that right? OX5 is actually shit. Yeah, all good. Yeah, leave those out for now. Okay, so we're now going to get the Okay, now we can just start assigning it straight out of our buffer. So the next one is going to be let's just get the, I think just our plain documentation should be good. So command, yep, command type is a uint, so we can just go equals uint of 8 of the next byte along, which is index 10, and then we can start going along from here, only if we know what it is. So look at all the different ones. Oh, constants. Yep. So for these command types, we know that we don't need to do anything. The next one along will be, well, actually in this, we know the next one is going to be a time signal because that it actually says that in our example. So we can, this is, yep. And then we know that we've got a 5, yeah, we know that we've got the 5 bytes left over. We might need to call it CMD buffer or something, I'm not sure. Oh. Save that there for now. So we know that the next value come up is going to be, let's have a look, our command, next value is going to be a uint 64, which in wire format is actually, okay, splice commands, time signal is a splice time, splice time, there we go, is this structure here. which is really just is 33 bits. So okay, so now what we can do is we can check. So we can, well, we can do two ways of, I think the more correct way would be to read the next byte, check if the flag is set, and then decode the timestamp in there. I'll just decode that 33-bit integer. So our next byte is at index 11. So let's check the next, the very next bit. So if buff of x, what is that? Is that 40? I'll just look up. Five, 6, 7, 8. 80, okay. So then we know that the next so we know that we now read the 33-bit timestamp. So that'll be, okay. And then our time signal, well, actually let's read our timestamp first by reading in all those, the next bytes. So tempted now to, just for clarity and instead of needing to keep up with all this index, we could actually just get a new slice, because it doesn't actually do any reallocations. I think the runtime handles that for us. So CMD buff actually is from I've got the length. I'll get that here. I think we have a function for this. Really what we should use. Although I think I could just really easily use the one, two, three, four, five, and then we can now set the field in our struct. So cmd time signal equals SCTE. Right. And then we can just set an error here. Check if oh yeah, no, I will have a string there, yeah. A string method on the and then finally we can set the command, good to go. Oh, this command, yeah, its command type has its own type. So what are we missing here? We're missing something. Apparently I'm just going to check again that we've got, slice command length is 5. Oh, this is not the correct, we want this. Wrong buffer. Now let's see. Oh no, of course, no, that's a different issue. Yeah, so we've got command type is, yeah, so maybe we do have something, yeah. So there is something wrong with the tier that maybe messes up with working out what type of command we have. So what we'll need to do is, we're gonna have to go backwards. Yeah, I think so. I'm going to be very sure that we're reading for the correct example. RFG. Yeah, I mean, yeah, okay. We've got everything else correct.